Good evening to everybody. My name remains Timothy. I am the chairman, board of trustee, Timar Programming Consults. This night, we want to continue our training on deep learning with Python. Today date is 13th day of May 2024, which marks day 11 of our training. Let me hand over microphone to the tutor tonight in person of Salau Ayobami. Please take charge.
Okay, so good evening, everyone. I hope we can all hear my voice. So I just want to confirm. So if there is nobody hearing, so
We can hear your voice clearly.
um, okay, good. So today we are going to be talking about how to feed a deep neural network. So and I will be sharing my screen now. Comment, please. Comment, please. Okay, let me share my screen. Okay. I think we can all see my slide clearly.
Yes, we can.
Yes, we can.
Okay.
Yes.
So um, we are going to continue from where we stopped. So though we did some practical stuff in the last class, but in this class we are going to be looking at some terminologies and some ways and some things to look out for when we are actually dealing with deep learning models. So now we want to look at the proper way of feeding a deep neural network. So, and we are going to be looking at a lot of things that actually pertains to deep learning model. So, to start with, we are going to look at some essential concepts when it comes to a feeding a deep neural network. So, want to look at gradient, um, descent, iterative process, learning rate, and loss function. So now, when we talk about all these things, I think in the last class we drew some particular graph that has to do with loss and the number of epochs. So, and we're able to see that as the loss is reducing, then the number of epochs increases. So ideally, for a deep learning model, this is the ideal way it should go. So, but in some certain cases, some deep learning model always misbehave due to some certain things, which can be the gradient descent function, can be the iterative process, or it can be the learning rate that causes it, or the loss function itself. So we are going to be looking at some certain things that can actually influence a deep learning model to learn very well, and the ones that are also things that also affect it not to learn very well. So we are going to look at the number one thing is called pass or a backward pass, which is learning in artificial neural network, and it has to do with transversing through all neurons of a neural network. So that's what the pass does. Pass has to do with going forward and coming backward. So it's just like we have a neural network now. So now it feeds it in with all the features, then it also takes it back as well again to be able to confirm if it has actually learned very well from the feature. So, and a pass, it might be time consuming considering the number of hidden layers So depending on the hidden layer, so it can be time consuming. So now, for example, here, this feature that we're seeing, a man holding a phone, you can see the feature is being passed through a artificial neural network, and this is a neuron. Yeah, so it passes through this neuron. You can see, and we have this hidden layer. This is hidden layers. Yeah, so it passes through here. So, and before you know, then for it to move from this point to this point is called a forward pass. So the feature going through the whole neural network itself and going to the end of the neural network, which is the output at the end here, is what I call a forward pass. So that's one concept that we are going to look at. So now the second one is also called batch. And batch is a subset of the training set, which is usually called mini batch. So, and the goal of that subset is feeding the neural network with a limited number of instances iteratively. So, it's not like, for example, if you are training 10,000 data points, you can't just, all the 10,000 data points cannot just go inside. It won't just go inside the neural network. So how do they go in? They go in batch by batch. So the the neural network, based on the training data set, the neural network takes the data points in batch, it segments them into batch. So for example, here you can see the training data set as a whole here, and we can see we have batch one, which is usually to batch one, batch two, batch three. So this is three batches. So which means that we are going to feed the whole neural network three batches of the training data set. So it goes in the first time, second time, the third time. So which is for the batches. And the batch is also the number of data used in one forward or backward pass as well. So now the batch size, which is the number of cases collected from the training set. So it's also called the number of cases collected from the training set. So we can have batch one, batch two, batch three, and the batch depends on the complexity of the model that we're trying to build. So some certain cases, 10 batches is okay, some 20 batches, some 100 batches, depending on the model or the data set itself. So that's the second terminology, which is called batch. So now another one is called iteration. Now, what is an iteration? It is a backward and forward pass of a batch of data. So which means that when we talked about a batch, a batch goes into a neural network itself. So not all the old trained data set. So now this batch, it's going in into the neural network and also coming back as well, which is a forward pass and a backward pass. Is called iteration. So an iteration is just like for in a deep learning model where we have some set of data, which is a batch, goes in, feed it into the neural network, and each of those in the batch we have data points. They all pass through the neurons, each neuron separately, having different weights. So and they go through it and get to the end, and they also come back as well. So, and the number of iterations, what does it mean? Is the number of passes, each using a batch size number of instances. So, the number of iterations is just like saying, okay, we have so batch, so we have 20 batch. So that means the number of iterations is that, okay, the number of passes that we are using each batch size as the number of instances, whereby if we have 20 batches, we have 20 iterations. Yes, that's it. So, and that actually has to do with the forward and the backward pass for a batch of data. So, and we may need calculations for this based on the data that we are dealing with, depending on the size of the data. So, for you to be able to determine the batch size and also the number of iterations, it also depends on the data, like I said. So, we are also going to move to another terminology, which is epoch. Now, this epoch, I think in the last class, we talked, I think we plotted, uh, I think accuracy plot and loss. Okay, I think we plotted loss and epoch, accuracy and epoch. Yes. So, and you can see epoch is always on the x-axis. So that epoch, what does epoch means? It comes up almost often than not, and we have to define the number of epoch depending on the architecture you want to use. Either you want to use a recurrent neural network, you want to use a simple convolutional neural network, or you want to use faster recurrent neural network, fast recurrent neural network. So you have to define the number of epoch. And what does it mean? It means that passing the entire data set forward and backward only once. And when we say forward and backward only once, I will explain that in a bit. So an epoch is the number of times the algorithm walks through the whole training set, and one epoch contains data size over the batch size iteration. So that is the way to calculate epoch. Epoch means data size over the batch size. So I will show us an illustration here just now. Just come, please. So can we still see my screen, everyone? Okay, I think
Yes.
we can.
Maybe
Okay.
you can
So
close
now,
your
basically,
screen a little bit.
okay, I think let me show you this. So now, if you look at this, I have a batch size of what? A batch size of 4 here. You can see this batch size of 4, and the number of epochs here defined is 10. So, but that's not the case now. So now the point there is this, is that in this place we said um, that one epoch contains the data set size divided by what? The batch size. So now if you want to get the number of epoch, you look at this. Let me show us this so understand what I'm trying to say. So now look at this here. So why is it that we have 625? So during the training step, this is the first epoch. This is epoch one. We have 625 here. So, and the total data set I have, the data is 3,125, or let me say 3,400 as a whole. So this number divided by the batch size, which is this, divided by the data set size, will give me the the iterations. So the number of iterations. So that's why we have 625 iterations here that is going to go in. I defined the number of epoch as 10 here. So which it's eventually completed in these instances here. So I'm just trying to show us something here. So now this is where I'm going. Let me put it back here. So now when we say epoch, epoch means that, okay, the architecture itself should go through the data set 10 times. That's if you define the number of as 10. That means all data sets should be fed into the architecture. It's just like saying, let me give you a very simple example. Just like saying someone wants to learn how to do something. For example, maybe you want to learn how to, let's say, learn a trade or learn a skill. You know, the number of times you try and do it, actually going to, you have to, it gives you the higher chances of knowing that thing better, and, you know, having to retain the memory and understand what exactly that thing is. So if you do something once, it's not enough for you to understand the concept of that thing. So that's why if you want to train a deep learning model, the epoch is also a determining factor of whether your model will be able to generalize very well in the real world. Because if you use a very small epoch, then you are not actually trying to let the model, how do I put it? You won't allow the model to learn the patterns inside the whole data set itself. So you are telling the model, go through the whole entire data set 10 times, 10 times. So, and that's not enough. So, and in reality, if you want to train a deep learning model, the ideal number of epochs you must use, if it is a model you want to deploy in the real world, at least you must use 1000 epoch. 1000 what? Epoch. So I repeat that again. Now, this is where the problem is. Let me go back to this place. Now, this is where the problem is. And the problem is this. I have, I trained this and I use 10 epoch. I have 3,125 images. So I used 10 epoch. It used approximately, that is, okay, it used 5 hours for just 10 epoch. And that's due to the fact that the architecture of my PC. My PC is 16 gig RAM and is 1 terabyte space and is Core i3. You got what I'm trying to say? And it's used um, 5 hours just for 10 epoch. What if I want to use 1000 epoch or 100 epoch? So what amount of time is it going to take? So that's why I said that most of us, we can't use the system we are using currently. Can't use it for any deep learning thing because on the and when I was running it, it was my system was seriously, hanging. Was seriously hanging. I could not do anything. I just left it there, so I could not touch or do anything in the system. So that's that about the epoch. So and the epoch size is just like the number of times the data set should pass through the architecture for it to be able to learn better. So there's something we need to note. So the batch size and number of batches are not equal. Take note of that. I don't say batch size and number of batches. They are not they are not equal. So batch size means you are specifying, okay, this is the number of batch that we want. But number of batches is different. So number of batches comprises of the number of data points in a batch. So now setting a batch size is essential as we cannot pass the whole training set into the artificial neural network at once. It's not possible. So you have to specify. So and the final batch may contain fewer samples than the other batches depending on the number of data points in the whole data set. And also, the whole training set should be passed to the artificial neural network multiple times, which means the number of epochs. That's what we mean by that. And the more number of epochs you can see, the more learning processes. So there's no magic rule for choosing the right number of epochs and batch size. So, but best practice demands that the epoch size should be very large and the batch size should be reasonable. So that's one thing we should note. So as time goes on, when we do some certain things with some practical, we tend to see why we choose some certain number or some as the epoch and the batch size as well. So now let us see an example. So now, for example, if we have 10,000 images of human face as a training data set, just something like this. And we now said the batch size, we said the batch size should be 500. So which means that 500 images will be going into the artificial neural network. You get what I'm trying to say? We go into the artificial neural network. We go into the artificial. So which means that we have 500 images. So now if you divide 500 divided by 10,000, that should give us 5 divided by 100, that's 20. So which means that it will take 20 bar like 20 times for the whole these whole images before it goes to the artificial neural network once, 20 times, and that's the number of iteration. So if we divide the data set of 10,000 samples with the batches of size 500, we will have to wait for 20 iterations to complete one epoch. So that's what that means. So that if 500 divides 10,000 and we have 20, so which means that it will take 20, that's 20 iterations. That means all the whole images for each before it goes through the whole architecture itself, it will have to complete one epoch, which means that for it to complete one epoch, it has to take 20 iterations to do that. So 20 iterations before all these images will be fed into the artificial neural network all at once, 20 iterations, and which might take time. So because of maybe it might be due to the complexity of the data itself. So now, what is hyperparameters? So we already talked about epoch, iteration, batch size, and so on and so forth. So what is hyperparameters? So now, variables and parameters to define. Now, one thing there is that the structure of an artificial neural network and the training configurations for an artificial neural network. So these two things are very important when it comes to a deep learning model. You want to build a deep learning model. The structure of your artificial neural network and the training configurations as well. And the structure of the artificial neural network means that, well, how many hidden layers should you have? Okay. Um, how many hidden layers? Should it be 3? Should it be 4? Depending. The training configuration for the artificial neural network, the batch size, number of iteration, number of epochs, etc., etc. So it is so important to set the hyperparameters before training the network, because one of the main factors to gain magnificent results and accurate predictions is by considering the structure of the artificial neural network and the training configurations for an artificial neural network, just like we have pointed out the batch size, batch sizes, number of epoch, the iterations, etc., like that. So we need to define them. So that's what I call the hyper parameters. So the parameters that we need. So now, still under hyper parameters, first thing we need to consider is the network structure, which is related to hyper parameters. So now, under hyper parameters, we have number of hidden layers, network weight initialization, and activation functions. So now, the thing there is how to tune the number of hidden layers. Is asked for the number of hidden layers, adding hidden layers until the error does not improve in the test is a best way of tuning or increase or making sure that the hidden layers is okay. So because when we will still, I'll still explain what all these are. It's talking about the hidden layers. So, and how do we tune the hidden layers is we said until the error does not improve in the test. So which means that there's no change again. And we need to know that having too many layers is as inefficient as too low layers. So the layers must not be too many and it must not be too small as well. So when the hidden layers are too many, it will cause overfitting or it will cause underfitting. So and it must be moderate. So these are to consider. Now another thing is the network weight initialization. So using different weight initialization schemes according to the activation functions might also work. So might also help to improve the network weight. And we should take note that uniform distribution might be a good idea in so many cases when it comes to how to tune or how to set up a network with initialization. Another one is the activation functions, which has to do with when we are trying to set up the architecture a, of a neural network. So now choosing proper activation functions according to their functionality and usage. And when we say functionality and usage, now there are some certain cases where some activation functions are very proper and some we don't need them at that point. So we need to choose carefully. And also we need to know that Using a particular type of activation function on all layers will result in improper outcomes. So because we are using, let me say, ReLU, we now want to use ReLU on all the whole layers. It might actually cause overfitting, or it can cause underfitting as well. So the second one about hyperparameters is training algorithm related hyperparameters. So now the related hyperparameters are the learning rate, the batch size, and the number of epochs. Now, how do we tune the learning rate? Now, considering the effect of low and large learning rates in the artificial neural network performance, so if we see that the validation is starting to deviate away from the training and they are not trying to converge together, then that means we need to adjust the learning rate. So, and we need to take note that decaying or adaptive learning rates are usually preferred. And there's a reason for that. When we say decaying or adaptive learning rates are usually preferred, is because there are some certain model that needs adaptive learning rates, which means that the learning rate needs to be changed at interval when it enters inside a another epoch. When it has entered the second epoch, third epoch, 100th epoch, we need to adjust the learning rate so that they won't be overfitting or underfitting as well. So another one is the batch size. Now, the batch size, we can try 32, 64, 128, 256, and so on. But the most common one is 256. Yes, very common, 256. And 128 also is common. But depending on your data size, that's what you can choose. Or you can tend to choose any batch size that you want to choose. But also, the batch size affects the learning rate as well. It affects the performance of the model. Now, another thing is the number of epochs. So increasing the number of epochs and checking the validation accuracy is very important, because now the main thing there is this, is that for any model you want to train, the model will be training fine, and the model might be training and getting closer to 99.9%. But in a case whereby the validation is starting to drop or not moving closer to the training accuracy, then we need to adjust or increase the number of epoch so that that can be compensated for. So that's one thing also to note. We will see all these things in action. So before I move forward, is there any question before I move ahead?
Is there any question,
Hello?
please? I think there's no question. We can proceed, please. We can proceed,
Okay, sir.
please. Yeah.
So now we're going to look at some important things. There are some important things we need to note, is that hyperparameters values are used to control the overall learning process. That's one thing we need to note. And they cannot be directly trained from the data. They can't be directly trained from the data. Values that we need to set in order to allow our model to be able to perform very well, or for us to get a better output. That's what we need to note. And model parameters like weight, coefficients, etc., are fetched from data. They are fetched from data. Model parameters like weight, coefficients, they are fetched from the data itself. And hyperparameters are manually used to estimate their values. I used to estimate their values. So, and tuning of hyperparameters lead to minimized loss functions and optimized model. That's the main essence of hyperparameters, to tune them. When we have an optimized model, it is a result of a tuned hyperparameters. That means the batch size, number of epochs, and so on and so forth, and the number of layers, hidden layers. So all those things affect the optimization of a model. And a good practice for tuning them can be as follows. The model definition is one of it. Sampling possible hyperparameter values, which means playing around with a lot of values to see which one is going to give us what we want. And also evaluation and cross validation also matters. So evaluation and cross validation in the sense that if I use the same hyperparameter and for RNN and CNN, it's not possible that we have the same outcome. So those are what are cross validations and evaluation. We want to evaluate, we can compare two architecture together using the same hyperparameters, or we can compare the same architecture together varying different hyperparameters. So those are one of the ways to evaluate. So you change the batch size incrementally and the number of epoch incrementally. So the accuracy you get and the loss you get, you tabulate it. From there, you'll be able to plot it and see which one is okay. So, but it's time consuming as well. It's time consuming depending on the number of data depending on the data size. If it is 10,000 images, it will take time to do such things. So that's why we are saying we need a higher computing power, a laptop that has a very high GPU, a very good GPU, good architecture. So those are things that will actually help us. You might just actually get a laptop and just when you start training your model, you just leave it, but make sure that the power doesn't go away from it because it will take time. It just take time. So to do that, some might take days, some might take weeks for them to learn. So depending. So now hyperparameters, how to tune them. Now we can simply build a model for each possible combination of the hyperparameters, just like I said. So build a model for each possible combination of the hyperparameters. Just like I said, we have different models having different values of different hyperparameters. So that's one way to do that. Another one is grid search. So which has to do with it iterates on all different permutations of values to select the appropriate one. So it just goes around permutating and select the most appropriate one. And also it might be inefficient in some certain scenarios. Might be inefficient in certain scenarios. For example, this is hyperparameter one. We have values 1, 2, 3, 4, 5. Hyperparameter 2, 0, 9, 18, 27, 35. If you look at the result and compare them, so here we have 1 and 0. Here we have 1 and 9. So it will just keep going and going, just combine and permutate them. So these are just going to be the result. So, but it might be inefficient in some certain cases. Another one is the random search. This one has to do with providing statistical distribution for hyperparameter. For example, random sampling. So has something of this nature whereby the hyperparameters has to choose between random numbers between 1 to 5 and also random number between 0 and 35. So, but it depends on the use cases whereby we can use grid search or random search. So now when we now want to compare grid search versus random search. So this is the one in blue is grid search, and while the one in green is the random search. So the grid search is this: it creates a grid whereby to actually take note of the important features, and when it takes note of the important features, so it's now actually help us to also pinpoint the unimportant feature as well. So this axis is the important feature, axis is the unimportant feature. Is going to show them together, and whereby you are going to know which one is important and which one is not important. So, and the same thing goes for the random search as well. All right, it also helps us to highlight the important feature and also the unimportant feature as well. So, but there are some mathematical explanation for all this. So I'm not going to go into it because I don't want to bore us. The main thing there is how to use them, which we'll still look at when we go into more practical very soon. But not today. Tomorrow and next tomorrow. So now we want to now look at overfitting. What is overfitting when it comes to deep learning model? So now we'll just look at some three scenarios. So when we consider the deep neural network model below, we have the three. So the goal is finding a model that fits data samples with an acceptable error. So now, if you look at this model one, this model is too tight, which means that what it can actually is trying to say that it can generalize very well and knows exactly what is going on here. So, and this model in reality is not acceptable. This because it's not possible for this type of model to be able to predict on unseen data perfectly like this. So it's not possible. So now another one is the okay. I'm going to see my screen.
Yes,
The
now.
second one is okay. The second model
We have less
is
than
the
10
good one.
minutes.
And when we say the
Less
good,
than 10 minutes for this class to end. So
okay.
we'll do another
So
week.
the second model is the good one, whereby it tries to say that okay, yes, I can generalize but not overfit. So this is not no, there's no overfitting here and there's no underfitting here. And why in this case there's this is overfitting, and in this case this is underfitting. So this model does not fit the data itself. But while this actually fits, and this one overfits it. So, and the one with the minimum acceptable error is model 2. Yes. So this is what is acceptable in reality. So now, if we not consider, like I said, when we are talking about the acceptable error, so this one overfits. So the network is memorizing some of the training data in this case here. So it's memorizing it. So that's what it's trying to do. But in this case here, it's trying the model is trying to generalize and to be able to try and understand the pattern. It's not trying to, it's trying to understand the pattern, the underlying pattern there, so that you can be able to generalize on unseen data. Why this one is underfitting. So in the case where we can have, in some certain case, when you start training deep learning models, you might fall into this situation and this situation. And in most of the cases, I can tell you for sure, you always fall into most of the time. You always fall into this pit hole, and there's a reason for that. And the reason is because of the hyperparameters. So, but it takes and of the data set and the lapses in collection of the data itself also will affect and will cause overfitting. So, and there's one thing we need to note when we are training deep learning models is your data must be very, very credible. If your data does not represent reality to a certain extent, then you can't, you have, all you will always have is overfitting. It will overfit. There's nothing you can do about that. It will always overfit. So now let us now talk about the concept of overfitting. So we'll be able to look into it generally. So uh, the concept of overfitting is just like generalizing problem in ML. So we look at that, and the model is not trained to solve general problems. So, and accurate predictions on the training set, but inaccurate on unseen data. You can see that's for overfitting. You need to look at this. So, in the case whereby you are training a deep learning model and you're having an accuracy of 97%, 98%, 99% for the training, and for validation, you are seeing 60 something percent, 50 something percent, then there is a problem. The problem That problem is called overfitting. Overfitting. So if you try and use that type of model in reality, you will be inaccurately uh, predicting on unseen data. And that type of model can be very, very misleading. Another one is a complex model containing extra parameters and data that is not captured in the training process of the model. That also can cause overfitting. Another one is detecting the relationship in training data that are not held in general. So that also can cause it. So maybe your data is not representing some certain things that has to be contained in it, and you just ignored it and you just feed in the data because you want to quickly get results. It will cause overfitting. So fitting the line instead of finding the trend is also another problem again in the case of machine learning this time around. So you want to fit the line instead of finding the trend. Just like I said, it's not about the line itself. We don't want we can't have a part. There's no perfect model anywhere. But what we want is something that can actually help us, understand the trend, understand the pattern. So that's just what we want. We don't want a perfect model, and there's nothing like a perfect model. So and also, we want to talk about concept of overfitting. It might be called high variance in some certain cases. High variance. So that means that real data are highly varied from what has been trained. That is also another thing that has to do with overfitting. Okay. How many minutes more do we still have? So I'm trying to check
Like 3 minutes
if
more,
that was not
like
cut.
3 minutes
Okay.
more
The
for instance. So I can give you another
okay.
like
The
like
concept of okay. The concept of underfitting as well is we need to understand it because when we get to when we start training some model, when we go to the practical, that's when we appreciate all these things because it will actually help us and prepare our mind that okay, when you start seeing some funny things, so immediately you will just have to do what? You say, no, 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 let me stop this thing. This thing is, there's a problem from somewhere. So it's not generalizing very well. So when in a case whereby the training and the validation are not much more closer to each other, as the training is 92%, the validation should be 90%. Something of such nature. Yes, they are moving closely together. They are moving together. So in the case whereby the training first move from 80, 90, we now have validation moving from 40 to 50. There's a problem already. There's a big problem. So we need to actually go back and look at our hyperparameters, the batch size, the number of epochs. So the number of iterations, all those things, and the number of hidden layers, the structure of the whole artificial neural network itself. We need to look at it and get to understand. So that we will not waste resources and train a model that we will not use. So that's one thing about it. So the concept of underfitting is that the model cannot provide accurate predictions even and that one is even worst, very, very worst. And it's unable to find the capacity to learn data fully. So it doesn't even understand what is so, and the model could not learn enough patterns from the data or capture the dominant trend and might be called high bias in some cases. So, the model is highly biased towards as well. So, that's one thing about underfitting. So, and this can be very misleading. So, I will train us and teach us how to know when we have underfitting um, in our deep learning model while we are training it, and when we have overfitting while we are training as well. I hope we get that. So when we want to know that there's underfitting is when the training first move from let's say from 70% or let's say from 80% to 90%. From 90% it now drops down to 60% and is now dropping to 40 and is now picking up again. There's underfitting. So it's just moving around. So it's not understanding the trend itself. So it's not actually capturing the trend. So that's when we tend to know that okay, something is wrong. This is underfitting. So I hope we understand. I hope we understand that. I think we still have
Yes, we do, sir.
time. Okay. So another thing to note is the primary purpose of all machine learning models is to generalize well. And as we want the error to become smaller with more iterations, the process of overfitting detection should be based on the errors. So I will explain this. Now, we should always try to find a trend instead of fitting the line. You should take note. And training with one epoch will lead to an underfitted model. So the number of epochs also determine if a model will be underfitted or overfitted as well. So, and the training flow changes as underfitted to optimum to overfitted. So we need to always know when, okay, the model is already at the optimum and we can stop the training. So that's one thing that is also important. Or before we know it, from underfitting, then it keeps training and learning. It understands the pattern in the old data. And when we still leave it to keep training, before you know it, then it starts overfitting. So in some certain cases, this is just the flow from underfitting to optimum to underfitted. And underfitting is as bad for the generalization of the model as overfitting as well. None of it is good. Underfitting and overfitting is very bad. So how to avoid overfitting? Okay, I think I still have time. How to avoid overfitting? We have method one, which is training the artificial neural network with more data. That's number one. So we need to capture the essence of the purpose of what we are trying to do. So which means more data is needed. So and it has to do with reducing the capacity of the model to overfit a training set. Training the model with more data with which increases the generalization, and also data augmentation is a similar process. So we still talk about that data augmentation. So another one is multiple neural network. Using a multiple neural network can also aid us in averting case of overfitting. So which means running several artificial neural network in parallel on the same training set and using different initial weights and configuration, and also comparing their error with the error of their average also will help on the long run. So let's move to the next one. Now, the third method is constraining model complexity. So which has to do with decreasing the complexity of the model and making the artificial neural network smaller, which means removing layers and
Can,
reducing the
can
number
we
of
make
neurons.
can we make this one more larger? I mean, go to slide so and show it to us.
So constraining model complexity, which means decreasing the complexity of the model and making the artificial neural network smaller. So that has to do with removing layers that if the layers are too much, it might cause overfitting. So I can remove the layer or reduce it, which tends to reduce the number of neurons, and avoiding the network to catch all data points. So the network itself, we don't need it to catch all the whole data points. It can lead to overfitting. Pruning it by removing nodes until it achieves a suitable performance. And one thing there is that any magic rule for the amount of simplification. So there is none actually. So it's just the more you try and play around or you train some models, so and you play with the hyperparameters, then the better you tend to understand the way and the way they operate and why the learning rate also has to do with it, why the learning rate is going that way and some other things. So it depends on the number of deep learning models someone trains as times goes on. So the one I is early stopping. So now early stopping is just a simple approach applicable to all artificial neural network, which use gradient descent. So and But before going further, we need to know what is regularization. So early stopping has to do with, okay, when we start, when there is a room for overfitting, or when overfitting wants to set in, we just come in and we just stop and move on to the next epoch, so that there won't be anything like overfitting. So regularization has to do with just trying to reduce the error by fitting a function on the training set and finding patterns in the training data and generalize them as much as possible. So, but not trying to overfit them. And how can it help? It prevents complex information from being learned, which leads to overfitting, and limiting the optimization problem to discourage complex models, and also improving generalization of a model on the test data. That's what regularization does, and it's always, we can incorporate it in our neural network, in our artificial neural network. So it can actually help us avert the risk of having overfitting. Avoiding overfitting, we said early stopping. So we said that we will have to stop the training when the generalization error tends to be increasing. So, and the error measured with respect to development set often shows a decrease followed by an increase. So, which means this is what that is trying to say. For example, let me use this. For example, if we have our, let's say this is the number of epoch. Epoch is going to be on, okay, epoch. And let us say this is the loss here. So now, ideally, in in a real world scenario, the loss is supposed to be decreasing this way, with respect to the number of epoch and be going. So, but in the case whereby we have a situation whereby it goes from here this way and it now keeps increasing, so there's a problem already. So at this point, this number of epoch, uh, at this number of epoch, the training needs to be stopped so that it doesn't further continue. So this gives room for what I call overfitting. So because the generalization error tend to be increasing, and which will cause problem on the long run. And another thing there is that when it comes to, this is for the loss, but when it comes to accuracy, in the case of accuracy, but when we are using loss and epoch here, this is what they call the loss graph. So it shows the error between the loss and the epoch. So we'll be able to know if our model is actually training very well. In the case of accuracy and epoch, we always have 1.0. This is 1. I say this is 5. So 1.0 means 100. So we'll put it that way. And this is 0. So in this case, the accuracy can start from here. Let's say this one is the benchmark, which is the maximum. So it can start from maybe 70 and be moving and come to this way and just be moving closer to 100%. So, but in the case whereby it moves this way, it was going and we're having a issue where it is coming down, then there's a problem. So this is showing us the point where it starts converging. It means there's a problem either with the number, the batch size, the learning rate, the epoch, or some other things at all, or maybe the data itself, the actual data we are using, something is wrong with it. So that's where we'll be able to know. So these are things that we can use to know. Now, another one is this again. When it comes to, okay, something of this nature. Okay, let's say for example, we there's a plot when we are training our model. We have the train and validation. Something we call training and validation. Training and validation. So they are always plotted together, side by side. So now, in this case, let's say the training goes this way, and so the y-axis is going to be the loss, and the x-axis is going to be the epoch. In this case, we can have the let's say the validation. Validation can be coming as a dotted line, just this way, and moving very close alongside moving. So which means as its training is validating, so which means that the model itself can generalize on new data, on unseen data. So this in reality makes more sense. But in the case, sorry about this. In the case whereby we have something like this, okay, let me use this. Let me use it again. I have something like this where we have the this thing. So we have this goes this way, and we now see our that's this for the training, the tick lines for the training, the dotted lines for the validation. And where validation start moving and deviating and is going this way, is going and is now moving up. So there's a problem. So this gap alone is trying to tell us that there is a problem with the data or some of the hyperparameters. So this will give room for overfitting. So for this to be averted, we need to go back. When we see something of, we need to go back and check reset some certain things. So let me try and okay, let me erase all of it. Okay. Okay, so now, like I said, so one thing also we need to do is the iteration. So we need to be monitoring the model performance and using a trigger to stop the training when we see some anomalies there. So those are some things that we need to take note of. So now let's move to the next slide. Another okay, this was what I was trying to talk about. So how to avoid overfitting, early stopping. So normally where we have the training, where we have the loss and the number of iterations, which is epoch. So if the training is this, and then we start having issues whereby we start moving overfitting. So or validation start going away from the training itself, then we have what they call overfitting. When the case whereby they are almost, so let's say, let us put it this way. As in this case, whereby it goes this way continuously and it keeps going this way. Let's say it keeps going this way. So this is underfitting. So it's not moving closer. But in this case, whereby I just move away, this is overfitting. So there's a problem like that. So that's one thing we should take note of. So those are the ways to actually take note if we have overfitting or underfitting. So take note of that. So, and we need to stop the training when we have something of this nature. Yeah. So we need to stop it and try and check some things back. So another one is drop out. So another way to avoid overfitting. So a per-layer regularization method that randomly ignores some nodes is called dropout. And randomly setting some activation functions to 0. So which means that the parameters just like randomization probability, setting some an example like 0.2, so can also help in some certain cases. Is different for some use cases. So I'm making the training process noisy, encourage the network to learn instead of memorizing the patterns. So that's also can make us avoid over overfitting. And also the dropout reduces the capacity of the network thinning. So and this network thinning, it has to do with a lot of things. We will see it in practical when we start doing some certain practical, when we start training some images, I want to train some images. And dropout can be used on all or any of the hidden layers. You can use dropout. So dropout, this is just an example of it. We remove some certain neurons or some nodes, remove them away, and we only consider some few ones. So now the learning paradigms that we have is this. We want to talk about learning paradigms. Now, do different artificial neural network and particularly deep neural network learn in a unique manner? That's a question. Do they learn in a unique manner? Now, definitely not. So it all depends on the learning task. So the learning task is going to actually dictate how they learn. So now, for the learning paradigms, for deep learning, we have supervised learning. We have the unsupervised and we have the reinforcement learning. So now, in the case where we have supervised learning, so that has to do with learning with a teacher. So tagged data. So that's supervised. So where you have a teacher to supervise you. So a set of paired inputs and outputs, and the goal is to producing desired output for each input sample. So we have input and we expect some output. So and as well, it has to do with providing feedback on the quality of solutions. So and applications in classification, regression, pattern recognition, etc., actually relates to this type of learning paradigm, which is supervised learning. So here we can see here we have the input of raw data, the supervisor is here. So the training of the data set and the desired output, so whereby we can get the algorithm works on it and we have processing then the processing and we have the output. So that's for the supervised. Now, for the unsupervised, yeah, we have the input data plus the output data plus the error, which is the cost function. So trying to learn, it has to do with trying to learn patterns from untagged data, which means unlabeled data. So we don't tag it, we don't. So we are trying to see if our model can, the algorithm can learn um, and know what is what from the input data we have given it, and also with the output data for it to be able to match them and okay, which one is to which one and which one is not which one, so you can be able to cluster them. So the case study is organizing photos in a gallery. So and another one is to know that deep neural network are mainly impactful on structured data. So that's one thing there. So and for this one here, we can see here that it actually created a cluster for them. A cluster one, cluster two, cluster three. That's for unsupervised learning. So another one is reinforcement learning. And reinforcement learning tends to be the best type of learning because it is has to do with trying to maximize the total cumulative reward, and which means an agent learns to achieve a goal in an environment. So based on reward and penalty. So the model itself should find the solution with a maximized reward and finding a solution with the lowest possible cost in the future. So it may be even with error. So it has an advantage is that it can be it has experience from hundreds of evaluations. So and the pictorial visualization here shows it that the environment is the environment and then the dog. So whereby the environment the things that the agent needs to do. So and the agent is going to be a task that is being carried out, an observation, and the action it gives out. So it's going to be penalized or it's going to be rewarded based on the actions. So that's for reinforcement. So it's the best. So now, still on the reinforcement learning, one thing there is this is that we have the agent, we have the reinforcement. It thus flows this way. We have the we have reward. The it's the thing that we agents to do. So we state something instructions or it can be anything. So action of the agent will now make us say okay because you did it right, you have a reward or several rewards, and based on that, give you another task and you do it, and based on that, I give you not.
All right, you can continue.
Okay, was this where I was out?
No, go back.
No, not this slide.
No,
Is it this slide?
no. I mean, you have been talking
Back,
since.
back.
Yes, this is where you were.
Is it this
Yes,
slide?
here.
Yes.
Okay.
Yes.
So what I was talking about is we are talking about reinforcement learning that the environment will always reward the agent based on any action that we say it should do. So and based on any action that we say it should carry out. And if the action is right, then there's always a reward. That's reinforcement learning. And I said it's the best learning so far and so good. It's actually very good. So, and in the practical usability of it is in the case of autonomous vehicles, self-driving cars. And the AI module there learns from the systems awards and penalties for unseen scenarios. So that means that it actually has a reinforcement plan whereby it can learn from the environment, and based on that it carries out actions, and the actions, if it is rewarded, then it actually is going to be very happy to continue doing that. But whereby it doesn't, we don't reward it, then it now readjusts itself and try to use that as well to learn as well. So that's the case of reinforcement learning, and which has to do with the case study of autonomous vehicle. So what I was trying to say in the last slide, which is the last slide, is that this is the roadmap we are following, and the roadmap is very simple. We already talked about the fundamental concepts. We already talked about neural networks. We already talked about training process, and I've given some. We have looked at some examples, and we talked about working with data, look at different type of data, images, audio, videos, and so on. We look at the sources of some data and deep learning and data. So today we talked about training concepts, hyperparameters, and learning paradigms. We said we have the supervised, unsupervised, and reinforcement. And also, tomorrow we'll be looking at some certain things which has to do with codes and libraries that we can use to train deep learning models. Example is TensorFlow and Keras. Another one is PyTorch. So, and we'll be looking at some platforms that we can use to train deep learning models. For example, we can use Google Colab because it has more computing power, unlike even if we want to use our own personal computer, it might give us issues. And we're going to look at deep neural network types. So this is where we are going to focus more now. So this will actually take a lot of time. And the reason why it's going to take a lot of time is because of how well we can um, we can assimilate very fast. That is one thing that is going to determine the key part of it. You need to understand this part very well. And when we are done with this part, then we will now revisit what we said when we said go and choose a topic or a research interest, an area that interests you that has to do with deep learning. So you will use it as your project, and when you are done using it as your project, then you can now turn it into a paper if you want to publish it. So this is our roadmap, and we are done with one, two, three. We are moving to four, and then the last part, which is five. So, and this is where we will eventually end the training, and there's a reason for that. So, but for this part, it is for interested people that want to go further and do their project, but you can submit your project, we will critique it, and we will send feedback to you so you can work more on it. And if you need any advice, you can do that. And if you want to turn it to paper, that is after your project has been validated that okay, it is okay, then you can turn it to paper if you want to. So these are some references where we can get to understand some things that has to do with epoch, iterations, hyperparameters, everything we talk about today, overfitting, underfitting. So, and do we have any questions? So, for call it a day.
Dr. Ajayi, you raised your hands up last time. Dr. Nuden,
Thank you very much, sir.
you're welcome.
My question is on data augmentation. Is it ethical? Is data augmentation ethical in deep learning?
Okay.
Take for instance, I have a small data set. Is there any way I can increase it, the size of the data set, using data augmentation, so that I can have
Yes, sir.
a?
It is very ethical. Can you hear me,
Okay,
sir?
I can hear you.
It is very ethical, and yeah, and you can do that if you have a small data set, and
Okay,
if you see that the cost of getting the data or very large sample size is going to be very cost and stressful,
okay,
then you can augment your data. And there are different ways to do that. You can do what they call there's something they call flipping, rotation, and we have there are different ways to it that whereby we can create a
okay,
very large sample size. And I'll show
okay,
us working code that can do that for us.
okay.
So
All
where
right.
we'll see it in action.
So
So that's
in
very is
addition,
ethical.
it is very, very ethical. One can use it. So since you have small data, you can augment it to become more larger. So it's acceptable on the side.
Okay. Thank you.
Dr. Ajayi, Dr. Hakim Arebigwe, are you all in the
Yeah,
house? Your question,
yeah,
please.
good evening.
You're welcome, sir.
Yeah, please, I will need that slide. This
Okay.
night slide, please, is very important. Thank you.
All right.
Okay, sir.
Noted. Other questions, please. Okay. Since there's no question, I think by now we can call it a day. So
Hello,
Dr.
sir. I'm here. I'm here with you, sir.
Okay, who is there?
This is Dr. Laisi. Dr. Laisi.
Okay, yeah, please go ahead.
Thank you very much for
Yes, sir.
to talk. My question is, are we still in the Google Colab environment? And also, the tutor mentioned
Okay.
something earlier. We use 5 hours to run the program. So what specification is it telling us now? The specification.
That's a big problem. I could not do any work today. I've been on this work since on Friday. On Friday. So that's how serious it is. And I started training it this morning. I was at to 11 this morning, and it ended up to 5 this evening. So you can see that that's 10 epoch. 10. What if I want to use 100? What if I want to use, and I said at least 1,000? This system will crash instantly. It's as simple as that. So that's why I'm saying computing
Dr.
power.
Lasisi,
So
Dr.
Yes, sir.
Lasisi,
I'm saying computing power.
Yes, sir.
Dr. Lasisi.
Yes, sir.
If you want to go more deeper in deep learning, we call it deep learning.
Mm.
Deep. Anything that is deep is called deep. So there is a work I've been doing for the past since last week Wednesday. There's a work I've been doing on a system since last week Wednesday. I've been carrying my
And
system
you have
from office
internet.
to home, from home to office, from office to home, and I've
You
not
dare
gotten.
not switch off the system. You can't switch
Yes,
it off.
and I've not
It's
gotten
very
results.
risky.
And if you switch off the system or your system collapse here, that's the end. That's
That's
the
it.
end to that system.
That's the end.
That's the end. It
I
will
have a
never wake
question.
up again. That system will never wake up
Hello.
again. So that's how it is, yo.
Okay.
Aha.
So what's your question, sir?
Okay. Can I say something, please?
Okay, please say
Yes, sir.
something.
Hello, sir.
You're welcome.
We are listening.
Yeah.
Right.
Yeah. So the you said you're running the code for forever, or for like many hours. Now, my question is the following:
Okay.
are you running it in your local machine or in Google Colab?
In
Any
my
of the
local
two.
machine, sir.
It depends.
I can't use Google Colab because of I'm using data. That's one thing. And just look at it, the amount of data it will use, because I'm using computing power. They are computing
No,
power. With my data that compensate for it.
sorry.
Okay.
Google Colab, because actually I have not investigated Google Colab, but
Okay.
I feel that for Google Colab to exist for deep learning, it means that it's a high performance computer somewhere. It's a supercomputer that runs.
Exactly.
Sorry, that runs in parallel, which means that it will not take much time on Google Colab. So,
Yes,
right. And for them to have done that, it means that in the first place, you're not even supposed to think of using your Core i3 machine to run deep learning. So that's why
use it,
Google
but depending
exists.
we can run it, but depending on the task. There are some lightweight deep learning models you can run depending on the image type, image size. Those are the things. But in the case whereby it is exceeding some certain things, the normal specification to run a deep learning model is the system must be an NVIDIA system. And in short, I don't know if I've heard about a system called MSI. I don't know. Some of us must have heard about the name. An MSI system.
Yes.
That system is specifically designed for deep learning. Specifically designed for deep learning. So there are some
machine.
yes.
GPUs.
So they are specifically designed. There are some systems that are specifically designed.
So, hello.
We are with you.
So that's what I'm saying. So I think obviously deep learning is not meant for CPUs; it's for GPUs, and that's why this platform
That's the point. So it's GPU. So that's the point. That's why there's enough GPU on Google Colab that we can plug into that aids the listening very well. So, but how can I use this thing? But if I want to run anything on Google Colab, I will need data, because you must be online in order for it to keep on running. So if you disconnect your data, it automatically be asking you to reconnect. and that will be a problem while your model is training.
I think sorry, I think because there is a principle and idea for all these online platforms for doing this kind of work. There must be a way that Google Colab, let me repeat again, I've not checked it. There must be a way for Google Colab, since it's an intensive computational thing. So there must be a way for it to allow you to log out.
Hello, doctor.
You won't log
You don't use MOS for something you have not confirmed.
out.
No, no, no.
I've used
I'm
it.
with doctor.
Hello, sir.
I'm
I've
with
used
doctor.
it.
Hello.
I have used it
What
times without
doctor is
number.
saying
So
is
this
very
is the way
clear.
it works. This is the way it works. The way it works is this. If it won't log you out, but there is something they call timeout. It might time you out and ask you to reconnect. And there are reasons for why it will do that. So for it to ask you to reconnect, it means it has disconnected from the GPUs that is using,
Sorry,
because you can't just be idle. Listen, sir, you can't be idle not using the free GPUs that they are giving you. So they have to allocate it to another person or another resource to other people. So if you are idle for a long time, it will disconnect you from the resources. That's one thing about Google Colab. So, and also another thing, if you have internet fluctuations, your internet is not strong, it will actually disconnect you. So those are the downside about it. And another thing is power supply. If you are training a model and your battery is not strong, and you are training it and power supply goes off, that's also another issue again. So it doesn't log you out, it just disconnects you from the resources. And for you to continue using, you have to reconnect back. So if you are idle for up to 10-15 minutes, it disconnects you. So that's the way it works.
So you are saying if you are disconnected, your job will
I
not
hope you
continue to run?
get it, sir. So that's just the way
Your job will not continue to run to pause.
it
I'm
doesn't
saying from
log
instance
you
here.
out.
You see,
Okay.
people that
Maybe
design.
this is because we are
Hello,
using
It will
a
not
free vocabulary.
continue
hello,
to run.
hello. Let me just come in there. The people that
Okay, we are with
design
you.
Google
It
Yes.
won't
Colab
continue to run.
in, from the European countries where Google Colab was developed, they don't buy data anyhow like the way we buy it in Nigeria here. So they are 24-hour online, internet connected. So hope you get me now. So not like Nigerian
sir,
people
can I,
just buy data for 2 gig, 3 gig, and we are just buying it for buying sake. In
so
other
they
countries, so they are 24-hour connected. That's just it. Let me end this meeting. Let me end this so I can stop the recording. So on this note, I appreciate everybody for your contributions. Thank you very much. Special thanks to the tutor and those that are the contributors as well. Thank you very much. God bless you.